Hello, and welcome back to the quiet side of science. If you're settling into bed, stretching out on a couch, or simply letting the day slowly fade behind you, you're in exactly the right place. Tonight we're going to wander through one of the most curious questions modern science has ever encountered. It is a question that begins not in distant galaxies or inside powerful particle accelerators, but somewhere much closer. It begins inside your own awareness. Right now, as you listen to these words, something remarkable is happening. A collection of atoms inside your brain is somehow producing a rich inner experience. You are hearing a voice. Perhaps you're picturing ideas. Maybe you're drifting through thoughts of the day, or simply noticing the slow rhythm of your breathing. Physics is very good at describing the atoms involved in this process. Scientists can measure electrical signals moving through neurons. They can track molecules sliding across microscopic channels in cell membranes. They can even watch patterns of activity across different regions of the brain as you think, remember, or imagine. But there is one small detail that remains surprisingly mysterious. None of these descriptions explain why any of it should feel like something from the inside. Why should a pattern of electrical signals in the brain create the sensation of hearing a voice, remembering a childhood home, or watching the colours of a sunset? Why does the universe contain experience at all? For a long time, scientists assumed this mystery would eventually dissolve as neuroscience advanced. After all, many puzzles that once seemed magical have slowly become understandable through careful research. Lightning turned out to be electricity. The movement of the planets followed the quiet mathematics of gravity. Even the origin of the stars can now be traced to the slow collapse of clouds of gas drifting through space. Yet consciousness remains strangely resistant to explanation. And then, during the 20th century, another scientific revolution quietly complicated the story even further. Physicists studying the smallest building blocks of nature began to notice something deeply unusual about reality itself. At the level of atoms and subatomic particles, the universe does not behave like a collection of solid objects moving along predictable paths. Instead, it behaves more like a cloud of possibilities. A single particle can exist in multiple potential states at once. Only when the particle is measured does one definite outcome appear. This phenomenon is described by a mathematical object called the wave function. Rather than telling us exactly where a particle is, the wave function describes a range of possibilities. It is a kind of probability landscape, a map of everything that might happen. When scientists perform a measurement, that landscape suddenly narrows to a single result. Physicists often describe this change as the collapse of the wave function. But here is the curious part. The equations of quantum mechanics describe how the wave function evolves over time with extraordinary accuracy. These equations have predicted experiments with astonishing precision for nearly a century. Yet the theory never clearly explains why the collapse occurs. Something about the act of observation appears to transform a cloud of possibilities into a definite event. This puzzle became known as the measurement problem, and it remains one of the deepest open questions in physics. At first glance, this may seem like a purely technical issue, the sort of detail that only theoretical physicists might worry about during long afternoons at a chalkboard. But the implications reach far beyond the laboratory, because eventually every chain of measurement leads to a human observer. A detector records a signal, a computer processes the data, a screen displays the result. Light reaches the eyes of a scientist. Electrical impulses travel through the brain, and, finally, somewhere within that brain, a conscious experience occurs. In other words, at the end of the measurement chain sits awareness itself. This raises a subtle but fascinating possibility. What if consciousness is not merely a passive witness to reality? What if it plays some role, however small or indirect, in bringing definite events into existence. Not all physicists agree with this idea. Many interpretations of quantum mechanics avoid involving consciousness altogether. Some suggest that the universe constantly splits into many parallel histories. Others propose that hidden variables quietly determine outcomes behind the scenes. But even these explanations leave us with a quiet sense of wonder, because the deeper scientists look into the structure of the universe, the less it resembles the solid clockwork machine that earlier generations once imagined. Instead, reality begins to look more like a delicate web of relationships, probabilities, and information. And somewhere, inside that web, conscious minds appear, tiny pockets of awareness, scattered across a vast cosmic landscape, quietly observing the unfolding universe. Whether consciousness is simply an emergent property of complex brains, or something more deeply woven into the fabric of reality, is still an open question. Tonight, we're going to explore that question together. We will wander through the strange territory of quantum physics, visit some of the most intriguing theories about the nature of consciousness, and meet a few of the scientists and thinkers who have dared to suggest that mind and matter may be more closely connected than we once believed. There will be paradoxes, there will be thought experiments, and occasionally there will be ideas strange enough to make the universe feel just a little more mysterious than it did a moment ago. But there is no rush. We will move slowly, the way good questions deserve, because sometimes the most fascinating discoveries in science do not come from finding quick answers, but from learning how to sit comfortably with the mystery itself. Let us begin with something very simple. Right now, as you listen to this voice, you are aware. You're aware of sound, of words forming meanings, perhaps of the gentle weight of a blanket or the quiet movement of air in the room. There may be thoughts drifting across your mind, memories appearing and fading, or images forming softly behind closed eyes. This inner landscape feels completely natural. In fact, it feels so ordinary that we rarely stop to examine it. But if we pause for a moment and look carefully, something about awareness becomes surprisingly mysterious. Consider the physical side of what is happening. Inside your brain, billions of neurons are communicating through tiny electrical pulses. Each pulse is created when charged particles move across microscopic membranes inside nerve cells. Sodium ions flow inward, potassium ions flow outward. Calcium signals trigger chemical messages to jump from one neuron to another. It is an intricate electrical conversation happening at astonishing speed. Neuroscientists can observe many parts of this process. With sensitive instruments, they can measure patterns of brain activity. They can see which regions of the brain activate when you hear a sound, recognize a face, or remember a song from childhood. From the outside, the brain appears as an elegant biological machine. But something curious happens when we try to move from those physical descriptions to the experience itself. Electrical signals can be measured, chemical exchanges can be recorded, neural pathways can be mapped. Yet none of those measurements explain why these processes should feel like anything at all. Why does a pattern of electrical activity produce the sensation of hearing music? Why does another pattern produce the feeling of sadness, curiosity, or calm? From a purely physical perspective, the brain is made of atoms obeying the same laws of physics that govern stars, oceans, and drifting clouds of gas in space. Atoms themselves do not seem to contain feelings, and yet, when arranged in the extraordinarily complex structure of the human brain, those atoms somehow generate the vivid theatre of conscious experience. This puzzle has fascinated philosophers and scientists for centuries. One way to approach it is through a simple thought experiment. Imagine a scientist who understands everything there is to know about the physics of the brain. This scientist knows the exact position of every neuron. They know the precise electrical patterns involved in seeing the colour red. They understand the chemistry of the retina and the visual cortex down to the smallest detail. Now imagine that this scientist has lived their entire life in a black and white room. They have studied colour scientifically, but have never personally experienced it. One day, the door opens and they step outside for the first time. For the first time in their life, they see a red sunset glowing across the sky. At that moment, something new appears. They have not learned any new physical information. All the physics was already known. Yet the experience of seeing red contains something that could never be captured by equations or measurements alone. The philosopher David Chalmers later described this puzzle as the hard problem of consciousness. The phrase does not mean the problem is difficult in a technical sense. It means that the problem is fundamentally different from other scientific questions. Most scientific problems involve explaining how a process works. For example, scientists can explain how the heart pumps blood. They can describe how muscles contract, how the lungs exchange oxygen, or how gravity pulls planets into orbit. These are sometimes called the easy problems of science, not because they are simple, but because they can be solved by analysing physical mechanisms. Conscious experience introduces a different kind of question. Instead of asking how the brain processes information, we must ask why those processes produce experience at all. Why does the universe contain the sensation of sound, colour, taste, and emotion? Why is there something it feels like to be alive? One possibility is that consciousness is simply an emergent property of extremely complex systems. In this view, when enough neurons interact in the right patterns, awareness naturally appears. This idea is somewhat like the way temperature emerges from the motion of many molecules. A single molecule does not have a temperature, but when billions move together, the concept of warmth suddenly makes sense. Perhaps consciousness works in a similar way. Yet even this explanation leaves a lingering mystery. Temperature can be measured directly. Thermometers record it as numbers. It fits comfortably within the framework of physics. Experience, however, remains private. You cannot measure the feeling of a colour directly from the outside. You cannot place the taste of chocolate into a laboratory container. Even the most advanced brain scanner cannot capture what it feels like to remember a childhood moment or hear a familiar voice. Consciousness always seems to exist from a first-person perspective. Only the experiencer can truly know it. And this simple observation leads to a quiet but profound realization. Every piece of scientific knowledge humanity has ever discovered has been known through consciousness. Every telescope image, every particle collision experiment, every line of mathematics has ultimately appeared within the awareness of a human mind. In that sense, consciousness is not just another phenomenon inside the universe. It is the medium through which the universe becomes known at all. For centuries, scientists assumed that consciousness would eventually be explained entirely by neuroscience. Many still believe this will happen. But during the 20th century, an unexpected development in physics reopened the discussion. When physicists began exploring the strange behaviour of quantum particles, they encountered a puzzle involving observation itself. In certain experiments, the outcome seemed to depend on whether or not a measurement was made. Particles behaved differently when observed. At first, this idea sounded almost philosophical, even mystical, but it emerged directly from careful experiments and mathematical theory. Some physicists wondered whether the act of observation might play a deeper role in the structure of reality. Most interpretations of quantum mechanics do not require consciousness to explain these experiments, but the question has never completely disappeared. Could awareness itself be part of the story of how reality becomes definite? That is the question we will gradually explore. For now, it is enough to notice the quiet mystery already present in our everyday lives. The universe is made of atoms and fields. governed by mathematical laws, stretching across billions of light years, and yet within certain arrangements of those atoms, a new phenomenon appears: the ability to experience, the ability to know, the ability to wonder about the universe that produced us. Perhaps the most remarkable thing about consciousness is not how mysterious it is, but how familiar. It is the background of every moment of life, so constant and gentle that we rarely stop to notice it. Like the soft hum of a distant machine that has always been running, awareness quietly accompanies every thought, every memory, every sensation. And somewhere within that quiet hum lies one of the deepest mysteries science has ever encountered. For most of human history, the universe seemed wonderfully predictable. If you threw a stone, it followed a clear path through the air. If you rolled a ball across the floor, it slowed gradually and came to rest. If you watched the moon rise above the horizon, you could expect it to appear again the following night. These patterns gave scientists confidence that nature followed consistent laws. Over time, thinkers like Isaac Newton transformed those observations into mathematical descriptions of motion and gravity. In this classical picture of the universe, the world behaves almost like a carefully designed clock. Objects have definite positions. They move along precise trajectories. If you know their starting conditions, you can predict where they will be later. This framework worked extraordinarily well. It allowed scientists to calculate the orbits of planets, predict eclipses, design bridges, and eventually launch spacecraft into orbit around the Earth. For centuries, it seemed that the basic structure of reality had been understood. But early in the 20th century, physicists began examining matter at extremely small scales, inside atoms and subatomic particles. And that is where things began to look strange. When scientists studied electrons, photons, and other tiny particles, they noticed something deeply unexpected. These particles did not always behave like tiny solid objects. Instead, they often behave like waves. Now waves are familiar things. Ocean waves rise and fall as they travel across water. Sound waves move through air, carrying music or speech from one place to another. Even light itself can behave like a wave, spreading out through space. But particles behaving like waves introduced a peculiar twist. A wave does not occupy a single point. It spreads out across many possibilities at once. Imagine tossing a pebble into a still pond. Ripples expand outward in circular patterns. The energy of the disturbance is not located at one precise point but distributed across the surface of the water. Something similar appears to happen with quantum particles. Instead of existing in one definite location, a particle can exist in a spread of potential locations simultaneously. Physicists describe this state using a mathematical idea called the wave function. Rather than telling us exactly where a particle is, the wave function describes the range of places where the particle might appear if we look for it. In simple terms, it represents a landscape of probabilities. One of the clearest demonstrations of this strange behavior appears in an experiment known as the double-slit experiment. The setup is surprisingly simple. Imagine a thin barrier with two narrow openings cut into it. These openings are the two slits. Behind the barrier is a screen that can record where particles arrive. Now imagine firing tiny particles such as electrons toward the barrier one at a time. If electrons behaved like ordinary little objects, you would expect them to pass through one slit or the other. On the screen behind the barrier they would form two clusters, corresponding to the two openings. But that is not what happens. Instead, the pattern that appears on the screen looks like a series of light and dark stripes known as an interference pattern. This type of pattern normally appears when waves overlap and interact with one another. It is the same pattern you see when two sets of ripples meet on the surface of water. The astonishing part is that the electrons are being fired one at a time. Each electron seems to pass through the experiment as if it were behaving like a wave spread across both slits simultaneously. Only when the electron finally arrives at the screen does it appear as a single localized point. This phenomenon led physicists to introduce a concept called superposition. Superposition means that before a measurement occurs, a quantum system can exist in multiple possible states at the same time. A helpful way to imagine this is through music. Think of a piano chord. When several keys are pressed together, multiple notes resonate simultaneously. The sound you hear contains all those notes blended into one harmony. In a similar way, a quantum particle can exist as a blend of multiple possible states at once. It is not choosing between them yet. Instead, it holds all those possibilities together like the notes of a chord. Only when a measurement is made does the system seem to select a single outcome. At that moment, the chord resolves into one note. The particle appears in one specific place, with one specific set of properties. Physicists describe this transition as the collapse of the wave function. Before measurement, the particle is described by a spread of possibilities. After measurement, only one of those possibilities remains. The mathematics describing this behavior is remarkably precise. Quantum theory can predict experimental results with extraordinary accuracy, often to many decimal places. Yet beneath that mathematical success lies a quiet conceptual puzzle. What exactly causes the wave function to collapse? What transforms a cloud of probabilities into a definite event? The equations themselves describe how probabilities evolve over time, but they do not clearly explain the moment when possibilities become reality. For many physicists, this question remains one of the deepest mysteries in modern science. At first glance, the issue might seem purely technical, a detail buried inside complicated mathematics. But the implications reach much further, because every measurement eventually involves an observer. A detector records a signal, a device processes the information, a screen displays the result, and eventually someone looks at the outcome. Some interpretations of quantum mechanics treat the measuring device as the point where the collapse occurs. Others suggest that the collapse may not happen at all, and that reality simply branches into multiple possibilities. But the simple question remains: what exactly counts as a measurement? Is it the interaction with the detector, the recording of information, or the moment when the result enters conscious awareness? These questions may seem abstract, yet they lie at the heart of how we understand the structure of reality. Because if the smallest building blocks of the universe exist as waves of possibility until something interacts with them, then observation itself may play a deeper role in the unfolding of physical events. And that thought leads naturally to the next puzzle. If observation matters, then we must ask what observation really means. As scientists explored the strange world of quantum particles, they gradually learned how to predict the outcomes of experiments with astonishing precision. The mathematics of quantum mechanics works beautifully. Physicists can calculate the likelihood that an electron will appear in a certain location. They can estimate the probability that a photon will pass through a particular filter. They can even predict how atoms combine to produce the colours of stars or the chemistry of life. These predictions come from a mathematical description known as the wave function. Rather than describing a particle as a tiny object sitting in one exact position, the wave function describes a set of possibilities. It is like a map of potential outcomes. In this map, each possible result has a certain likelihood attached to it. If you imagine the wave function visually, you might picture something like a soft cloud drifting through space. The cloud represents all the places a particle might be found if we look for it. Some regions of the cloud are thicker, meaning the particle is more likely to appear there. Other regions are faint, meaning the particle is less likely to appear. As time passes, the wave function evolves according to a precise mathematical rule. The probabilities shift and flow in a smooth, predictable way. In the language of physics, this evolution is governed by a fundamental equation often associated with the Austrian physicist Erwin Schrödinger. But the equation itself is not important for our story tonight. What matters is the behavior it describes. The wave function evolves continuously, spreading possibilities across space like ripples in water. Yet something unexpected happens when a measurement is made. When a detector interacts with a particle, the cloud of possibilities seems to vanish. Instead of a range of potential outcomes, we observe a single definite result. The particle appears in one place, not many. Physicists describe this transition as the collapse of the wave function. Before the measurement, the particle is described by many possible states. After the measurement, only one of those states remains. This sudden shift creates a conceptual puzzle. The mathematical rule that governs the evolution of the wave function is smooth and continuous. It never predicts a sudden jump, and yet measurements always produce clear, definite outcomes. It is as if the theory contains two different kinds of behavior. One rule describes the gentle unfolding of possibilities. Another rule describes the sudden appearance of a single reality. The first rule comes directly from the mathematics of the theory. The second rule seems to appear only when we observe the system. This tension became known as the measurement problem. To understand the puzzle more intuitively, imagine standing in front of a large painting that has not yet come into focus. At first, the image looks soft and blurry. Colours blend together in gentle patterns, suggesting many possible shapes. Then suddenly, as you step closer, the painting becomes sharp. The shapes resolve into clear objects. Where there was once ambiguity, there is now certainty. In this metaphor, the blurry painting represents the wave function, a collection of possibilities. The sharp image represents the result of a measurement, a single outcome that we observe. But in physics, the mystery is deeper than simply changing our perspective, because before the measurement occurs, the particle does not appear to have a definite position at all. The possibilities are not merely hidden from us, they are part of the physical description of the system itself. In other words, the wave of possibilities seems to be the real state of the particle before measurement. Only when the system interacts with something else does one possibility become actual. This raises an intriguing question. What exactly counts as a measurement? At first glance, the answer seems obvious. A measurement occurs when a detector interacts with a particle. For example, a sensor might register the arrival of an electron. A camera might capture the flash of a photon striking a surface. But if we look more closely, the situation becomes less clear. The detector itself is made of atoms. Those atoms follow the same quantum rules as the particle they are measuring. If the particle can exist in multiple states at once, then in principle the detector could also enter a superposition of states. In that case, the measurement might not produce a definite outcome yet. Instead, the particle and the detector could become linked, together in a shared quantum state containing multiple possibilities, and the puzzle continues. If the detector sends a signal to a computer, the computer is also made of atoms. If the computer displays the result on a screen, the screen is also a physical system. Each stage of the process is governed by the same quantum rules. So where exactly does the collapse occur? At what point does the cloud of possibilities finally become one definite reality? Physicists have proposed many different interpretations to address this question. Some interpretations suggest that collapse happens when a quantum system interacts with a large environment. The surrounding world effectively forces the system into one outcome. Other interpretations suggest that collapse never truly occurs at all. Instead, every possible outcome continues to exist in separate branches of reality. And then there is a more controversial possibility that some physicists have occasionally considered. Perhaps the collapse occurs when the result enters conscious awareness. Perhaps the act of observation itself plays a role in selecting the final outcome. This idea is far from universally accepted, and many scientists remain skeptical of involving consciousness in fundamental physics. Yet the possibility continues to appear in discussions about the foundations of quantum theory. Because the measurement problem leaves us with a simple but profound question. If the universe at its smallest scales is described by a cloud of possibilities, then what is the mechanism that turns those possibilities into events? And who or what performs the final observation? As physicists explored this puzzle further, they began to imagine increasingly elaborate thought experiments. Some of these experiments suggested that different observers might disagree about what reality looks like. And that strange possibility leads us to the next stage of the story. By the time physicists reached the middle of the 20th century, the measurement problem had become one of the most intriguing questions in science. Quantum mechanics worked extremely well as a predictive tool. Experiments repeatedly confirmed its results with remarkable precision. Yet the deeper meaning of measurement remained elusive. To explore the puzzle more carefully, the mathematician John von Neumann proposed a thought experiment. He suggested that we look closely at the entire process of measurement step by step, beginning with the quantum particle itself. Imagine a tiny particle moving through an experiment. Perhaps it is an electron travelling toward a detector. The electron interacts with the detector. When the particle arrives, it triggers a small physical change in the device. Maybe it produces a tiny electrical signal or causes a microscopic flash of light. That signal then travels into electronic circuits inside the instrument. The circuits amplify the signal and convert it into a form that can be recorded. From there, the information might appear on a screen. A small dot lights up at a specific location, indicating where the particle has been detected. Light from that screen travels outward through the room and reaches the eyes of a scientist. Photons strike the retina at the back of the eye. Nerve cells convert those photons into electrical impulses. Those impulses travel along the optic nerve and enter the brain. Finally, patterns of activity spread through regions of the brain responsible for vision and awareness. At that moment, the scientist becomes consciously aware of the result. What von Neumann noticed was something simple but profound. Every step in this chain is a physical process. The particle follows the rules of quantum mechanics. The detector is made of atoms that also follow quantum rules. The electronic circuits are built from materials whose behavior can ultimately be traced back to quantum physics. Even the neurons inside the brain are physical systems made of molecules and atoms. In principle, every stage of the measurement process could be described using the same mathematical framework. This observation creates a curious difficulty. If quantum mechanics governs all these systems, then each step in the chain could itself enter a state of superposition. In other words, the particle could exist in multiple possibilities. The detector could record multiple outcomes simultaneously. The screen could display several potential results at once. Even the brain, in theory, could be described as a complex quantum system containing multiple possible states. When these systems interact, they may become linked together in what physicists call an entangled state. Entanglement means that the states of the systems become correlated. Instead of describing each system separately, the mathematics describes them as one combined system. So the particle and the detector become linked. Then the detector becomes linked with the electronics. Then the electronics become linked with the screen. And eventually the chain extends all the way to the brain of the observer. At each stage, the quantum description could continue to include multiple possibilities. This is what became known as the von Neumann chain. It is a conceptual chain connecting the microscopic world of particles to the macroscopic world of human awareness, and it leads to an unsettling question. If every component of the chain obeys the same quantum laws, where exactly does the collapse of possibilities occur? Does it happen when the particle strikes the detector? Does it occur when the electronic signal is amplified? Does it occur when the screen displays the result? Or does it occur only when the scientist becomes aware of what happened? Von Neumann himself explored a radical possibility. Perhaps the final step in the chain occurs in consciousness. Perhaps the collapse of the wave function happens when the result enters awareness. This idea does not necessarily mean that the mind directly alters physical reality. Instead, it suggests that the boundary between quantum possibilities and classical events might lie at the point where experience occurs. Many physicists have been uncomfortable with this proposal. Science usually tries to describe nature without invoking subjective experience as a fundamental mechanism. Yet von Neumann's reasoning revealed something important. If we treat all physical systems consistently according to quantum mechanics, the measurement problem does not easily disappear. The chain of physical interactions can be extended almost indefinitely. Particle to detector, detector to electronics, electronics to screen, screen to eye to brain. At every stage, the same question returns. Where does possibility become fact? Later, physicists developed alternative approaches to avoid involving consciousness directly. Some proposed that interactions with the surrounding environment gradually destroy quantum coherence. In this view, a system loses its delicate superpositions when it interacts with many surrounding particles. This process is often called decoherence. Decoherence explains why quantum behavior becomes difficult to observe in large systems. Tiny particles can maintain delicate probability waves, but everyday objects interact constantly with their environments. Air molecules, photons, vibrations, and thermal energy continuously disturb them. As a result, the wave-like behavior of large systems becomes effectively hidden. Decoherence helps explain why classical reality appears stable and well-defined. Yet even decoherence does not fully resolve the measurement problem. It explains how quantum possibilities become extremely difficult to observe, but it does not clearly explain why a single outcome appears in our experience. The chain of observation still ends somewhere, and wherever it ends, something remarkable occurs. A cloud of probabilities becomes a single observed event. The world of potential outcomes resolves into one definite reality. As physicists continued to explore these ideas, some began constructing thought experiments to push the logic even further. One of the most famous of these experiments imagined two observers looking at the same event from different perspectives, and according to the mathematics of quantum theory, those observers might disagree about what has actually happened. This strange possibility leads us into one of the most fascinating paradoxes in modern physics. Imagine a small laboratory sealed inside a quiet building. Inside the laboratory stands a scientist performing a simple quantum experiment. Perhaps the experiment involves measuring the spin of an electron, or detecting the path of a photon travelling through an apparatus. For the scientist inside the room, the procedure is straightforward. The particle is prepared. The detector activates. A result appears. Maybe the instrument shows that the electron spin is pointing upward. Or perhaps it records the photon arriving at one particular location on a screen. From the perspective of the scientist inside the laboratory, the measurement has already happened. The wave of possibilities has collapsed into a definite outcome. The scientist writes down the result and continues the experiment. Now imagine that outside the sealed laboratory stands another observer. This second observer cannot see what is happening inside the room. The laboratory is perfectly isolated and no information escapes. From the outside observer's perspective, something unusual occurs. According to the mathematical rules of quantum mechanics, the entire laboratory can be treated as a single physical system. The electron, the detector, the scientist, and even the notebook used to record the result are all made of atoms. And those atoms follow the same quantum laws as the original particle. If the outside observer describes the system using the wave function, then the laboratory may still exist in a superposition of different outcomes. In one possibility, the scientist inside the room observes the electron spin pointing upward. In another possibility, the scientist observes the spin pointing downward. Both outcomes remain part of the mathematical description. From this external viewpoint, the entire laboratory exists as a mixture of possibilities. Inside the room, however, the scientist experiences only one result. For them, the outcome is definite. This difference in perspective creates a subtle paradox. One observer believes the experiment has produced a single clear result. The other observer describes the situation as a superposition of multiple possibilities. Both descriptions seem valid within the framework of quantum mechanics, and yet they cannot both represent the same reality at the same time. This thought experiment became known as Wigner's friend. It highlights a curious tension between two ways of describing the world. The first description belongs to the observer inside the experiment who experiences a definite outcome. The second description belongs to the external observer who treats the entire experiment as a quantum system evolving through probabilities. To make the situation easier to imagine, consider a simpler analogy. Suppose two friends are watching a mystery film. One friend sits inside a theatre and sees the entire movie unfold, including the final scene where the mystery is resolved. The other friend is waiting outside the theatre and has not yet seen the ending. From the perspective of the person inside, the story is complete. The outcome is known. From the perspective of the person outside, the ending still exists as a set of possibilities. They can imagine several different conclusions, but none has been confirmed. In everyday life, this difference disappears once the second friend enters the theatre and watches the film. But in quantum physics, the mathematics allows both descriptions to exist simultaneously. The inside observer sees a definite result. The outside observer describes a system containing multiple possible results. This situation raises an intriguing philosophical question. Whose description of reality is correct? Does the collapse occur when the scientist inside the laboratory performs the measurement? Or does the collapse occur only when the outside observer opens the door and learns the result? Some interpretations of quantum mechanics suggest that reality itself is relative to the observer. Different observers may legitimately describe the same system in different ways, depending on the information available to them. Other interpretations propose that both possibilities continue to exist in separate branches of reality. In that picture, the universe quietly splits into different histories, each containing one of the possible outcomes. Still other interpretations attempt to preserve a single objective reality by introducing hidden mechanisms that determine outcomes behind the scenes. Each of these approaches tries to resolve the puzzle in a slightly different way. Yet the Wigner's friend scenario remains powerful because it forces us to confront an uncomfortable idea. Observation in quantum mechanics is not as simple as it first appears. In classical physics, observing something does not fundamentally change the nature of reality. Looking at a planet through a telescope does not create the planet. It merely reveals something that already exists. But in quantum physics, observation seems to play a more active role. Measurements do not simply reveal properties. They appear to help define which properties become real. This does not necessarily mean that human consciousness directly shapes the universe. However, it does suggest that the relationship between observers and physical systems is more subtle than classical physics once imagined. Instead of a detached spectator watching a fully formed world, the observer may be part of the unfolding process through which reality becomes definite. This idea led some physicists to wonder whether the concept of an observer might need to be understood more deeply. What exactly counts as an observer? Is it any physical system that records information? Is it a measuring device interacting with a particle? Or does the chain of observation ultimately end in conscious awareness? As physicists continued exploring these questions, another remarkable discovery began to reshape our picture of reality. Particles separated by vast distances could become mysteriously linked in ways that seemed to ignore ordinary ideas of space. This phenomenon became known as quantum entanglement, and it suggested that the universe might not be made of separate objects at all, but of relationships connecting everything together. By the time physicists began examining the foundations of quantum mechanics more carefully, they had already encountered several strange ideas. Particles could behave like waves. Possibilities could exist simultaneously in superposition. Measurements could transform clouds of probabilities into definite events. Yet another discovery soon added a new layer of mystery. This phenomenon became known as quantum entanglement. To understand the idea, imagine two particles created together in a special interaction. Perhaps they are produced in a process where a single particle splits into two smaller ones. During this process, certain properties of the particles must remain balanced. For example, if one particle eventually spins in one direction, the other must spin in the opposite direction. At first, this does not seem surprising. If two coins are prepared so that one must be heads when the other is tails, then learning the result of one coin automatically tells us the result of the other. But quantum entanglement is stranger than this simple example. In classical situations, the properties of the coins are already determined before we look at them. They simply carry hidden information that we later discover. In quantum systems, however, the situation appears different. Before measurement, the particles may exist in a shared state, where neither particle has a definite value yet. Instead, the system contains a set of possibilities. The two particles behave as if they are part of a single extended system, even when separated. Only when one particle is measured does a definite result appear, and when that happens, the corresponding property of the other particle becomes fixed instantly, even if the particles are extremely far apart. To see why this surprised physicists, imagine the following situation. Two entangled particles are created together in a laboratory. Then they begin travelling in opposite directions. One particle travels toward a detector on Earth. The other travels toward a detector on a distant spacecraft drifting far beyond the Moon. When the scientist on Earth measures the particle, the result appears immediately. If the measurement shows that the particle's spin points upward, then the other particle must have the opposite spin, and according to the quantum description, that property becomes determined the moment the first measurement occurs. The strange part is that the second particle may be extremely far away. The two particles could be separated by kilometers or even light years, yet the correlation between them appears instantly. This feature of quantum mechanics troubled some of the greatest scientists of the 20th century. Albert Einstein famously referred to the phenomenon as spooky action at a distance. Einstein believed that the universe should obey a principle called locality. Locality means that objects are influenced only by things in their immediate surroundings. Information should not travel faster than light. But entanglement seemed to challenge that intuition. If measuring one particle immediately determines the state of another distant particle, how can that influence travel across space so quickly? Einstein and two colleagues, Boris Podolsky and Nathan Rosen, proposed a famous argument suggesting that quantum mechanics might be incomplete. They reasoned that the particles might carry hidden properties that determine the outcomes in advance. In that case, the measurements would simply reveal information that was already present. For many years, this remained a philosophical debate, but later experiments began testing whether such hidden variables could exist. Physicists developed careful experiments to examine the correlations between entangled particles. These experiments measured pairs of particles under different orientations and compared the statistical patterns of their results. The predictions of quantum mechanics turned out to be extremely specific. If the particles truly shared an entangled quantum state, their measurement outcomes would follow a certain pattern. If hidden variables determined the results ahead of time, a different pattern would appear. Over time, increasingly precise experiments were performed in laboratories around the world. The results consistently supported the predictions of quantum theory. The correlations between entangled particles were stronger than any classical hidden variable explanation could produce. In other words, the particles did not appear to carry predetermined answers. Instead, their properties seemed to become defined only when measurements occurred. And yet, even with these remarkable correlations, entanglement does not allow information to travel faster than light. Scientists cannot use entangled particles to send messages instantly across space. The outcomes remain fundamentally unpredictable. What entanglement reveals is not faster communication, but deeper connection. Two particles that were once part of the same quantum system continue to behave as if they share a single underlying description. Their relationship remains encoded in the structure of the wave, function. This discovery gradually led physicists to reconsider an assumption that had guided science for centuries. The assumption was that the universe is made of separate objects. In everyday life, this seems obvious. Tables are separate from chairs. Planets are separate from stars. People are separate from one another. But quantum entanglement hints that the deepest level of reality may not consist of independent pieces. Instead, it may consist of relationships. The properties of one part of a system cannot always be described without referring to the rest. In this sense, the universe may resemble a vast web rather than a collection of isolated things. Each thread connects to others, forming patterns that stretch across space. When one part of the web moves, the pattern of relationship shifts everywhere. This relational view of reality has influenced many modern interpretations of quantum mechanics. Some physicists have suggested that the fundamental ingredients of the universe may not be particles at all. Instead, the basic elements may be interactions, correlations, and flows of information. Objects might simply be stable patterns within that deeper network. And within that network, observers themselves are part of the system. The act of observation is not something happening outside the universe, it is another interaction inside the web. As these ideas developed, physicists began asking an even deeper question. If the universe is built from relationships rather than isolated objects, where does conscious experience fit within this picture? Is awareness merely a byproduct of complex brain activity, or could it play a more fundamental role in how reality becomes known? To explore that question, we must step for a moment away from quantum experiments and return to the mystery we began with, the mystery of consciousness itself. After exploring the strange behavior of quantum systems, it may seem surprising to return our attention to something as familiar as the human mind. Yet in many ways, consciousness may be the most mysterious phenomenon we encounter. Every moment of life unfolds within awareness. You hear sounds, you notice colours, you feel the gentle pressure of the chair beneath you, or the rhythm of your breathing. Thoughts appear, linger for a while, and then drift away. Memories surface unexpectedly, sometimes carrying vivid images from years ago. A certain melody can bring back a place, a voice, or a feeling that seemed almost forgotten. All of these experiences share a common feature. They are not merely physical processes. They are also something it feels like to experience them. There is a difference between a description of a process and the experience of living through it. To see why this difference matters, consider how science studies the brain. Modern neuroscience has developed powerful tools that allow researchers to observe activity within the brain. Instruments can measure tiny electrical signals traveling along neurons. Brain imaging techniques can detect which regions become active when a person performs different tasks. When someone looks at a bright red object, certain areas of the visual cortex show distinctive patterns of activity. When someone listens to music, other regions respond in ways that scientists can measure and analyze. Over time, researchers have built detailed maps connecting brain activity with different kinds of experiences. These patterns are often called the neural correlates of consciousness. The phrase simply means the physical processes in the brain that accompany conscious experience. For example, scientists might observe that when a certain network of neurons becomes active, a person reports seeing a particular color. When another network activates, the person hears a sound or remembers a familiar face. This progress has been extraordinary. It has allowed scientists to understand many aspects of perception, memory, and decision-making. Yet, despite these achievements, something curious remains unexplained. Even if we map every neuron in the brain and measure every electrical signal, we still face a deeper question. Why do these physical processes produce experience at all? Why does neural activity feel like something from the inside? The philosopher David Chalmers introduced a helpful way to describe this puzzle. He distinguished between what he called the easy problems of consciousness and the hard problem. The easy problems involve explaining how the brain performs various functions. For instance, scientists can study how the brain processes visual information, how it distinguishes different sounds, or how it stores memories. These problems are challenging, but they can be approached using familiar scientific methods. Researchers can measure neural activity, construct models, and test predictions. The hard problem is different. Instead of asking how the brain performs tasks, it asks why those tasks are accompanied by experience. Why does seeing light create the vivid sensation of colour? Why does touching a hot surface create the unpleasant feeling of pain? Why does listening to music produce emotions that can feel deeply moving? From a purely physical perspective, the brain is made of atoms arranged in extraordinarily complex structures. Those atoms follow the same fundamental laws that govern the rest of the universe. They interact through electromagnetic forces, exchange chemical signals, and transmit electrical impulses. But nowhere in those physical descriptions do we find the feeling of redness, the taste of chocolate, or the warmth of nostalgia. These qualities of experience are often called qualia. Qualia refers to the raw qualities of subjective experience, the redness of red, the bitterness of coffee, the quiet calm of a peaceful evening. They are the textures of awareness itself, and they appear to exist only from a first-person perspective. You can describe the physical properties of light that produce the colour red. You can measure its wavelength and energy. You can explain how the retina converts light into neural signals. But none of those descriptions capture what the colour red actually feels like. To illustrate this point, philosophers sometimes imagine a thought experiment. Suppose there is a scientist who knows everything about the physical science of colour vision. This scientist understands the biology of the eye, the chemistry of visual pigments, and the neural pathways that process colour information. However, this scientist has lived their entire life in a room where everything is black and white. One day, the scientist steps outside and sees a red rose for the first time. At that moment, something new appears. Even though the scientist already understood all the physical facts about colour, they now gain a new kind of knowledge. the experience of seeing red. This example suggests that conscious experience cannot be fully captured by physical descriptions alone. There seems to be an additional layer to reality, something that emerges when physical processes are experienced from within. Not everyone agrees with this interpretation. Some scientists believe that as neuroscience progresses, the mystery will gradually dissolve. They argue that once we fully understand how the brain processes information, the appearance of consciousness will seem less mysterious. Others believe the hard problem points toward a deeper limitation in our current understanding of nature. Perhaps consciousness cannot be explained entirely in terms of physical mechanisms. Perhaps it is a fundamental aspect of reality, something woven into the fabric of the universe itself. At this stage, these ideas remain speculative, but the question continues to intrigue both scientists and philosophers, because consciousness is not just another phenomenon within the universe. It is the medium through which every phenomenon becomes known. Every scientific observation, every experiment, every equation written on a chalkboard ultimately appears within the awareness of a conscious mind. In that sense, consciousness occupies a curious position in the story of science. It is both the object of investigation and the lens through which all investigation takes place. And this dual role leads to a fascinating possibility. If consciousness is deeply connected to the process of observation, and observation plays a mysterious role in quantum physics, then perhaps the two puzzles are not entirely separate. Perhaps the mystery of mind and the mystery of matter are somehow related. To explore that possibility, we must look more closely at what modern science can and cannot explain about the brain. Over the past century, scientists have learned an extraordinary amount about the brain. The human brain contains roughly 80 to 90 billion neurons, each connected to thousands of others through delicate branching structures. These connections form a dense network through which electrical and chemical signals travel continuously. Every thought, sensation and memory corresponds to patterns moving through this network. When you see a familiar face, certain visual regions of the brain become active. When you hear music, different networks respond to rhythm and pitch. When you recall a childhood memory, activity spreads across areas associated with memory, emotion, and imagination. Neuroscientists have become increasingly skilled at observing these patterns. Modern imaging technologies allow researchers to measure brain activity in remarkable detail. Functional magnetic resonance imaging, often shortened to the letters F, M, R, I, can detect subtle changes in blood flow associated with neural activity. Electroencephalography, sometimes called EEG, measures electrical signals produced by large groups of neurons. These tools have allowed scientists to create detailed maps showing which regions of the brain participate in different aspects of conscious experience. For example, certain regions of the visual cortex respond strongly when we see colours. Other areas respond to faces, movement, or depth. Similarly, areas of the temporal lobe help process language and sound, while regions of the frontal cortex participate in planning, reasoning, and decision-making. By comparing brain activity with reported experiences, researchers can identify patterns that reliably accompany particular mental states. These patterns are known as neural correlates of consciousness. The phrase simply means the physical activity in the brain that appears alongside conscious awareness. When someone reports seeing a bright red object, certain neurons in the visual system become active. When someone feels pain, different neural circuits respond. When someone falls asleep and dreaming begins, the patterns of activity across the brain shift again. These discoveries have brought us much closer to understanding how the brain processes information. But they also reveal an important distinction. A neural correlate is not the same as a full explanation. To see why, imagine listening to music through a radio. Inside the radio are circuits, wires, and tiny electronic components. If we examine the radio while music is playing, we can measure electrical signals moving through these circuits. We might discover that when a certain signal passes through a particular component, the sound becomes louder. When another circuit activates, the pitch changes. By studying these patterns, we could map the internal workings of the radio very precisely. Yet even if we completely understand the circuitry, that knowledge alone does not explain the origin of the music itself. The radio is part of the process, but the music is coming from somewhere else, transmitted through invisible signals. This analogy is not meant to suggest that the brain is literally receiving signals from outside the body. Most neuroscientists believe consciousness arises from activity within the brain itself. However, the analogy highlights an important point. Understanding the mechanism does not always reveal the full nature of what is being experienced. Mapping neural activity shows us how the brain behaves when consciousness is present. But the deeper question remains: why do these patterns of activity produce experience at all? Why does the brain generate the inner world of sensations, thoughts, and emotions? Some researchers believe that once we understand the brain in sufficient detail, the mystery will disappear. From this perspective, consciousness is an emergent property of extremely complex information processing. Just as temperature emerges from the collective motion of countless molecules, awareness may emerge from the coordinated activity of billions of neurons. Others believe that this explanation may not go far enough. They point out that even if we simulate every neuron in a computer model, the simulation might reproduce the behavior of the brain without necessarily producing genuine experience. A computer program can simulate the weather, predicting clouds and storms across an entire planet, but the simulation itself does not contain real wind or rain. In a similar way, a perfect simulation of brain activity might reproduce the patterns associated with consciousness without actually generating awareness. This possibility has led some thinkers to consider whether consciousness might involve something more than the information processing alone. Perhaps the physical processes inside the brain interact with deeper features of reality that we do not yet fully understand. At this point, such ideas remain speculative. But the question continues to inspire research and debate across many fields, including neuroscience, physics, and philosophy. Because the mind occupies a curious position within the natural world. On one hand, it clearly depends on the brain. Injuries to certain brain regions can alter personality, memory, or perception. Chemical substances that affect neural activity can dramatically change mood and awareness. On the other hand, conscious experience possesses qualities that seem difficult to capture through physical descriptions alone. Thoughts have meaning, experiences have texture and feeling, memories carry emotional significance. These aspects of mind do not appear easily reducible to the language of electrical signals and molecular interactions. And this tension between physical mechanisms and lived experience continues to motivate deeper exploration. Some scientists believe the key to understanding consciousness lies entirely within neuroscience. Others wonder whether the answer may involve new ideas about the nature of information, matter, or even reality itself. If consciousness is somehow connected to the fundamental structure of the universe, then our investigation may eventually lead beyond the brain to the foundations of physics. This possibility brings us to an intriguing crossroads. If the mind cannot be completely explained by current physical theories, perhaps we must reconsider our assumptions about the nature of reality. One possibility is that consciousness is not merely a byproduct of complex systems. Perhaps it is something more fundamental. Perhaps awareness itself is part of the deep architecture of the universe. When we look closely at the mysteries of consciousness and quantum physics, it becomes clear that our understanding of reality may still be incomplete. The brain produces thoughts, memories and perceptions through complex physical processes. Yet the existence of subjective experience remains difficult to explain entirely through those processes alone. Because of this, philosophers and scientists have developed several different ways of thinking about the relationship between mind and matter. One of the most widely accepted perspectives in modern science is called materialism. Materialism proposes that everything in the universe is ultimately physical. According to this view, consciousness arises from the activity of the brain in much the same way that heat arises from the motion of molecules. In this picture, the brain is an incredibly sophisticated information processing system. Neurons communicate through electrical signals and chemical exchanges. Networks of these neurons form circuits that process sensory input, store memories, and generate behavior. As these networks grow more complex, new properties emerge. Just as temperature emerges from the collective motion of countless molecules, consciousness may emerge from the coordinated activity of billions of neurons. From this perspective, the mystery of consciousness is not fundamentally different from other scientific puzzles. It simply reflects the enormous complexity of the brain. As our understanding of neuroscience improves, materialists believe that the mechanisms underlying consciousness will eventually become clearer. Another perspective takes a different approach. This view is known as dualism. Dualism suggests that mind and matter are two distinct aspects of reality. The physical world consists of atoms, energy, and the forces described by physics. Conscious experience, however, belongs to a different category. According to this view, the mind cannot be fully reduced to physical processes. Instead, consciousness may exist as a separate kind of entity that interacts with the brain. Historically, this idea has been associated with philosophers such as René Descartes, who proposed that the mind and the body were fundamentally different substances. In modern discussions, dualism appears in various forms. Some thinkers propose that consciousness might arise from non-physical aspects of reality, while others suggest that it may involve dimensions or properties not yet described by physics. However, dualism faces a difficult challenge. If mind and matter are separate, how do they interact? How does an immaterial thought influence physical neurons in the brain? This interaction problem has made many scientists cautious about adopting dualistic explanations. A third possibility has recently attracted renewed attention among some philosophers and physicists. This perspective is called panpsychism. The name may sound unusual, but the basic idea is surprisingly simple. Panpsychism proposes that consciousness, or at least the potential for experience, is a fundamental property of reality. Instead of appearing suddenly when brains become complex enough, consciousness may exist in some very simple form throughout the universe. In this view, the basic ingredients of nature might possess extremely faint forms of experience. These elementary forms of awareness would not resemble human thoughts or emotions. Rather, they might be more like tiny glimmers of experience, far simpler than anything we normally imagine. As matter organizes into more complex structures, these elementary experiences could combine and interact, eventually forming the rich consciousness we know. To visualize this idea, imagine a vast night sky filled with faint points of light. Each point glows softly on its own. But when many lights gather together, their combined brightness can illuminate an entire landscape. In a similar way, panpsychism suggests that the universe may contain countless small sparks of experience. When arranged in the intricate structure of a brain, those sparks might form the vivid awareness we experience as consciousness. Supporters of this idea argue that it may help address the hard problem of consciousness. If consciousness is already present at the most basic level of nature, then the emergence of experience in complex systems becomes less mysterious. Instead of appearing suddenly from entirely non-conscious matter, Awareness would be built from simpler forms that already exist. Critics of panpsychism, however, raise important questions. If elementary particles possess tiny forms of experience, how do those experiences combine to create a unified mind? How do billions of microscopic sparks merge into a single coherent awareness? This puzzle is sometimes called the combination problem. It highlights the challenge of explaining how simple elements could generate the integrated experience of a human mind. Despite these difficulties, the discussion continues to evolve. Some researchers believe that consciousness may be closely connected to information itself. Others suggest that the structure of reality may be fundamentally relational, meaning that properties arise through interactions rather than existing independently. These ideas echo themes that appeared earlier in our exploration of quantum physics. In entangled systems, particles cannot always be described separately. Their properties exist within relationships. Similarly, in the study of consciousness, experience may arise through complex networks of interactions rather than through isolated components. At this point, none of these perspectives has provided a final answer. Materialism, dualism, and panpsychism each attempt to explain the relationship between mind and matter in different ways. Each approach highlights certain insights while leaving other questions unresolved. But together they reveal something important. The mystery of consciousness may not simply be a small gap in our knowledge. It may point toward deeper questions about the nature of reality itself. If consciousness is connected to the foundations of physics, then understanding the mind may eventually require new ideas about how the universe works. And some scientists have already begun exploring that possibility. In the next stage of our journey, we will examine a bold proposal suggesting that the processes inside the brain may involve quantum phenomena. This idea, though controversial, attempts to connect the mysteries of consciousness directly with the strange behavior of the quantum world. For many scientists studying the brain, the most natural comparison for the mind has long been the computer. Computers process information using circuits that follow precise logical rules. Each operation transforms input into output according to well-defined instructions. These instructions form algorithms, step-by-step procedures that guide the machine through calculations. In many ways, the brain appears to operate in a similar fashion. Neurons transmit signals. Networks of neurons process information. Patterns of activity produce decisions and behavior. Because of this resemblance, some researchers have suggested that the brain may simply be a biological computer. According to this view, consciousness emerges when information processing becomes sufficiently complex. Yet the physicist and mathematician Roger Penrose began to question whether this picture might be incomplete. Penrose had spent much of his career studying the deep mathematical structures underlying physical theories, including the geometry of space-time and the physics of black holes. During his work, he became interested in a famous result from mathematical logic discovered by the Austrian mathematician Kurt Gödel. Gödel's result is often described as the incompleteness theorem. The theorem deals with systems of mathematics built from logical rules. In such a system, one begins with a set of basic statements called axioms. From those axioms, logical rules are used to derive new statements that can be proven to be true within the system. Gödel discovered something remarkable about these logical systems. He showed that for any sufficiently powerful system of mathematical rules, there will always exist certain true statements that cannot be proven using those rules alone. In other words, no fixed system of logical rules can capture every mathematical truth. There will always be statements that are true, but unprovable within the system. To understand the idea more intuitively, imagine a very large library containing all the books that can be written using a particular set of grammatical rules. The rules tell you how sentences may be constructed, and every book in the library follows those rules perfectly. Yet somewhere outside the library, there may exist a sentence that is perfectly meaningful and true, but which cannot be generated using the allowed grammatical patterns. The rules are powerful, but they cannot capture every possible truth. Gödel's theorem revealed a similar limitation within formal systems of mathematics. Penrose wondered whether this insight might say something about the human mind. When mathematicians explore new ideas, they often seem capable of recognizing truths that cannot yet be derived from existing formal rules. They see patterns, connections, and insights that go beyond mechanical computation. If the mind were simply following a fixed algorithm like a computer program, Penrose argued it might be limited in the same way as a formal mathematical system. Yet human reasoning sometimes appears to transcend such limitations. From this observation, Penrose proposed a bold possibility. Perhaps human understanding is not purely algorithmic. Perhaps the brain performs processes that cannot be fully described by ordinary computation. If this were the case, it would suggest that the mind may rely on physical mechanisms different from those used by classical computers. And that possibility led Penrose to consider the strange world of quantum physics. Quantum systems do not behave like classical machines. They exist in superpositions of possibilities. They evolve according to probability amplitudes rather than deterministic rules. Most importantly, the collapse of the quantum wave function remains one of the deepest puzzles in physics. Penrose began to wonder whether the processes responsible for wave function collapse might play a role in consciousness. Instead of treating collapse as a mysterious event, triggered by measurement, perhaps it arises from a deeper physical mechanism. Penrose suggested that gravity might be involved. In the framework of general relativity, gravity is not merely a force, but a property of space-time itself. Mass and energy influence the curvature of space-time, shaping the geometry through which objects move. Penrose proposed that certain quantum superpositions might become unstable when they involve significantly different space-time geometries. If a system attempts to exist in two states that correspond to different shapes of space-time, that situation might be physically unsustainable. Eventually, the system would resolve into a single state. This idea later became known as objective reduction. The phrase simply means that the collapse of quantum possibilities might occur as an objective physical process, rather than requiring an external observer. In this picture, nature itself selects a definite outcome when certain conditions are reached. To visualize this idea, imagine stretching a flexible sheet of rubber across a frame. As you pull the sheet in different directions, tension builds across its surface. At some point, the tension becomes too great to sustain multiple shapes at once. The sheet suddenly snaps into one stable configuration. Penrose suggested that something similar might occur within quantum systems interacting with gravity. Superposed possibilities might persist for a while, but eventually they must resolve into one definite reality. If such processes occur within the brain, they might provide a mechanism that goes beyond ordinary computation. Instead of operating solely through classical information processing, the brain might involve deeper physical events linked to the structure of space-time itself. This proposal remains highly speculative. Many neuroscientists believe that classical processes within neural networks are sufficient to explain consciousness. Others remain skeptical that delicate quantum states could survive within the warm, noisy environment of the brain. Yet Penrose's idea has continued to inspire discussion, because it raises an intriguing possibility. If human understanding truly involves processes that cannot be captured by ordinary algorithms, then the mind may be connected to deeper layers of physical reality, layers that we are only beginning to explore. In the next step of this journey, another scientist would attempt to connect Penrose's ideas with the biological structure of the brain itself, and that connection would lead to one of the most controversial theories about consciousness in modern science. As physicists struggled to understand the measurement problem, many different interpretations of quantum mechanics began to appear. Some suggested that collapse occurs when a measuring device interacts with a quantum system. Others proposed that the universe continually branches into multiple histories, each representing a different possible outcome. Roger Penrose explored a different possibility. He wondered whether the collapse of quantum possibilities might occur even without a measuring device or observer. Perhaps the universe itself contains a mechanism that eventually forces quantum systems to choose a definite state. To understand his reasoning, it helps to recall two of the great theories that describe our universe. The first is quantum mechanics, which explains how particles behave at extremely small scales. In this theory, particles exist as wave-like distributions of possibilities. Their behavior is described by mathematical structures that evolve smoothly over time. The second is general relativity, developed by Albert Einstein. This theory explains gravity not as a simple force but as the curvature of space-time itself. Mass and energy influence the geometry of space-time, shaping how objects move through the universe. For many decades, physicists have tried to reconcile these two theories into a single unified framework. Yet quantum mechanics and general relativity describe reality in very different ways. Quantum mechanics deals with probabilities and superpositions. General relativity describes smooth geometric structures that bend and stretch under the influence of mass. Penrose wondered what might happen when these two descriptions interact. In particular, he asked what occurs when a quantum system exists in a superposition of states that correspond to different shapes of space-time. Imagine a tiny object placed in a quantum superposition between two locations. In one possible state, the object sits slightly to the left. In another possible state, the object sits slightly to the right. According to quantum mechanics, both possibilities can exist simultaneously within the wave function, but according to general relativity, the mass of the object influences the curvature of space-time. If the object occupies two positions at once, the geometry of space-time itself would also need to exist in two slightly different configurations. Penrose suggested that this situation might create a kind of instability. Space-time may not be able to sustain multiple conflicting geometries indefinitely. Eventually, the system would be forced to resolve into one definite configuration. In this picture, the collapse of the wave function would not require an observer. Instead, collapse would occur as an objective physical process driven by the structure of space-time itself. This is why Penrose called the idea objective reduction. The word objective means that the process occurs independently of human observation. The word reduction refers to the reduction of many possible states into a single outcome. The proposal suggests that quantum superpositions have a limited lifetime. Small superpositions involving tiny differences may persist for relatively long periods, but larger differences, especially those involving significant mass or energy, may collapse more quickly. To picture this idea, imagine a thin sheet of rubber stretched across a frame. If you gently push the sheet in two nearby places, it may temporarily hold both shapes at once. But if you try to stretch the sheet into two very different shapes simultaneously, tension builds across its surface. At some point, the tension becomes too great, and the sheet suddenly snaps into a single, stable form. Penrose suggested that quantum superpositions might behave in a similar way. When the difference between possible states becomes large enough to distort space-time in incompatible ways, the superposition cannot remain stable. Nature resolves the tension by selecting one of the possible outcomes. If this idea is correct, it would provide a natural explanation for why quantum possibilities collapse. The process would not depend on observation or measurement. Instead, it would be built into the fundamental structure of reality. Penrose also speculated that such collapses might involve tiny bursts of fundamental events occurring throughout the universe. These events would represent moments when possibilities resolve into actual occurrences. Most of the time, these collapses would happen on extremely small scales and remain invisible to our everyday experience. But in certain complex systems, especially biological systems, they might play a more interesting role. This possibility led Penrose to consider whether such processes might occur inside the brain. If the brain contains structures capable of maintaining delicate quantum states, then the objective reduction of those states could potentially influence neural activity. In that case, consciousness might involve physical events linked not only to neurons and electrical signals, but also to the deeper geometry of space-time itself. At this stage, the idea remains speculative and controversial. Testing such proposals is extremely difficult because the effects would occur at scales far smaller than current experiments can easily observe. Many scientists remain skeptical that quantum superpositions could survive inside the warm, noisy environment of biological tissue. Yet the idea has inspired further research and discussion, because it raises a profound question. If the universe contains a natural mechanism that converts quantum possibilities into definite events, perhaps those events play a role in the emergence of conscious experience. To explore that possibility, another scientist would attempt to identify specific structures within the brain where such quantum processes might occur. And those structures are surprisingly small, hidden within the inner architecture of neurons themselves. To explore whether quantum processes could play a role in consciousness, we must look more closely at the architecture of the brain. Neurons are often described as the fundamental cells responsible for communication within the nervous system. Each neuron contains a central body, branching structures that receive signals, and a long extension that carries electrical impulses to other cells. Through networks of these connections, signals travel throughout the brain. But neurons are not simply hollow wires carrying electrical currents. Inside every neuron lies an intricate internal structure made of microscopic components that help organize the cell. One of the most important elements of this internal structure is a system of tiny cylindrical fibers known as microtubules. Microtubules are extremely small. Their diameter is only about 25 nanometers, which means roughly 40,000 of them could fit side by side across the width of a human hair. Despite their small size, they play essential roles inside living cells. They help maintain the shape of the cell, guide the movement of molecules, and support the transport of materials along microscopic pathways. You might imagine them as part of the internal skeleton of the cell. Just as the beams of a building help support its structure, microtubules provide stability and organization within the neuron. For many years, biologists considered microtubules primarily as structural components. They were important for the mechanics of the cell, but not necessarily involved in complex information processing. Stuart Hameroff began to wonder whether these tiny structures might play a more subtle role. Hameroff studied the effects of anesthesia on the brain. Anesthetic drugs have the remarkable ability to temporarily eliminate conscious awareness while leaving many basic biological functions intact. The heart continues to beat, the lungs continue to breathe, yet the vivid inner world of thoughts and experiences disappears. This observation raised an intriguing question. What specific structures in the brain do anesthetics affect when they turn consciousness off? Some studies suggested that certain anesthetic molecules interact strongly with proteins found within microtubules. This connection led Hameroff to consider the possibility that microtubules might be involved in the physical processes underlying consciousness. If microtubules participate in the organization of neural activity, perhaps they could also support more subtle processes occurring at the quantum level. Hameroff proposed that the internal arrangement of molecules inside microtubules might allow them to sustain delicate quantum states. Within these structures, certain protein components might briefly exist in superpositions of different configurations. In this picture, microtubules could function somewhat like tiny information processors embedded inside neurons. Instead of operating purely through classical electrical signals, they might involve deeper physical processes connected to quantum mechanics. When Roger Penrose learned about Hamerof's ideas, he saw a potential link with his own proposal about objective reduction. Together, they developed a theory known as orchestrated objective reduction. The word orchestrated suggests that the process is organized and coordinated by biological structures. Objective reduction refers to the idea that quantum possibilities collapse naturally through the physical mechanism Penrose described earlier. In this theory, quantum states inside microtubules would evolve for a short time, forming patterns of possibilities. Eventually, those possibilities would collapse through objective reduction. Each collapse would correspond to a tiny event in which multiple potential states resolve into one definite outcome. Hameroff and Penrose suggested that these events might occur many times each second within the brain. Each event could contribute to the unfolding stream of conscious moments we experience. In this view, consciousness would not arise solely from electrical signals moving between neurons. Instead, it would emerge from a deeper layer of physical activity inside the microscopic structures of those neurons. You might imagine it like a complex orchestra. The electrical signals passing between neurons form the rhythm section, setting the tempo and coordination of brain activity. Meanwhile, the quantum processes within microtubules add subtle harmonies beneath the surface. Together, these layers of activity might produce the rich experience we know as consciousness. The Orshaw theory remains controversial. Many neuroscientists argue that the brain is too warm and too noisy for delicate quantum states to survive. Quantum systems are often extremely sensitive to disturbances from their environment. Even tiny interactions with surrounding molecules can cause quantum coherence to disappear. This process, known as decoherence, typically occurs very quickly in large, warm systems. Because the brain is filled with thermal motion and chemical activity, some researchers believe that stable quantum states would collapse almost instantly. Hameroff and Penrose have responded by suggesting that the internal structure of microtubules might shield quantum processes long enough for meaningful interactions to occur. However, experimental evidence remains limited, and the debate continues. Despite the controversy, the theory has stimulated valuable discussion. It encourages scientists to consider how the physical processes inside the brain might connect with deeper layers of physics. Even if Orshaw ultimately proves incorrect, exploring such ideas helps expand our understanding of both neuroscience and quantum theory. And the question remains open. Could the brain, with its astonishing complexity, host physical processes that reach beyond classical computation? To examine that possibility further, researchers have begun studying a surprising field known as quantum biology. This field explores whether quantum phenomena might play functional roles in living systems. For many years, scientists believed that quantum mechanics belonged almost entirely to the microscopic world of isolated particles. In laboratories, quantum systems are often studied at extremely low temperatures, sometimes only a fraction of a degree above absolute zero. At such temperatures, atoms move very slowly. Disturbances from the surrounding environment are minimized. Under these carefully controlled conditions, quantum states can remain coherent for measurable periods of time. But living systems are very different. Inside the cells of the human body, molecules are constantly moving. Chemical reactions occur continuously. Heat and vibration fill the environment. From the perspective of traditional physics, this kind of environment seems hostile to delicate quantum states. Many researchers argued that any quantum superposition inside a biological system would disappear almost instantly through a process called decoherence. Decoherence occurs when a quantum system interacts with its surroundings. The interactions effectively spread information about the system into the environment, destroying the fragile coherence that allows multiple possibilities to exist simultaneously. In simple terms, the system loses its quantum character and begins to behave more like a classical object. Because biological cells are busy, dynamic places filled with constant interactions, it seemed unlikely that quantum effects could survive long enough to influence biological functions. Yet over the past several decades, scientists have discovered surprising hints that nature may sometimes use quantum processes even in warm biological environments. These discoveries gave rise to a new interdisciplinary field known as quantum biology. One of the most fascinating examples comes from the process of photosynthesis. Photosynthesis occurs when plants and certain microorganisms capture energy from sunlight and convert it into chemical energy. At the heart of this process lies a complex network of molecules that guide packets of energy toward a reaction center where chemical transformations occur. For many years, scientists believed this energy moved through the molecular network by simple random hopping. Energy would jump from one molecule to the next until it eventually reached the reaction center. But experiments using ultra-fast laser pulses revealed something unexpected. The energy appeared to travel through multiple pathways simultaneously, behaving more like a wave than a classical particle. In effect, the energy explored many possible routes through the molecular network at the same time. By doing so, it could rapidly find the most efficient paths to the reaction center. This behavior resembles a quantum process known as coherent superposition. Instead of moving step by step through a single route, the energy briefly exists as a distributed wave exploring multiple possibilities at once. Although this quantum coherence persists for only extremely short times, it may help make photosynthesis remarkably efficient. Another intriguing example comes from the mysterious navigational abilities of certain birds. Many migratory birds travel thousands of kilometers each year, navigating with astonishing precision across oceans and continents. Some researchers believe that these birds may sense Earth's magnetic field through a quantum process occurring in specialized proteins within their eyes. The proposed mechanism involves pairs of electrons whose spins become quantum mechanically entangled. When light strikes the molecule, it creates two electrons whose spins are linked in a subtle quantum relationship. Their combined state evolves in ways that are sensitive to the direction of Earth's magnetic field. Small changes in orientation could alter chemical reactions within the molecule, potentially providing the bird with a kind of internal magnetic compass. Although research in this area continues, experimental evidence increasingly supports the idea that quantum effects may play a role in biological magnetoreception. A third example comes from the study of enzymes. Enzymes are proteins that accelerate chemical reactions within living cells. They allow biological processes to occur far more rapidly than they otherwise would. Some experiments suggest that certain enzymatic reactions involve a phenomenon known as quantum tunneling. In classical physics, particles must overcome energy barriers to move from one state to another. Quantum mechanics, however, allows particles to pass through barriers that would otherwise be impossible to cross. It is as though the particle briefly slips through the barrier rather than climbing over it. In enzymatic reactions, tiny particles such as protons or electrons may occasionally tunnel through energy barriers within the molecular structure of the enzyme. This process can significantly increase the speed of certain reactions. These discoveries do not prove that consciousness arises from quantum processes, but they demonstrate something important. Quantum phenomena are not limited to isolated laboratory systems cooled to extremely low temperatures. Nature itself appears capable of maintaining quantum effects under certain biological conditions. Even if those effects persist only for very brief moments, they can influence the behavior of complex systems. For researchers interested in the nature of consciousness, these discoveries open an intriguing possibility. If plants can briefly maintain quantum coherence while capturing sunlight, and birds can use quantum processes to navigate across continents, perhaps biological systems are more compatible with quantum physics than once believed. The brain is an extraordinarily complex organ containing billions of neurons and trillions of molecular interactions. Within such complexity, subtle physical processes might occur that we have not yet fully understood. This does not mean that the brain necessarily uses quantum mechanics in the way proposed by theories like quark-or, but it reminds us that nature often surprises us. Processes once thought impossible within living systems sometimes turn out to exist after all. As research in quantum biology continues, scientists may discover new ways in which physics and life intersect, and as these discoveries unfold, they may help illuminate the deeper question that has quietly guided our journey: whether consciousness emerges purely from neural activity, or whether it reflects something more fundamental about the fabric of reality itself. Throughout the history of physics, scientists have often imagined themselves as observers standing outside the system they study. A physicist measures the motion of planets, records the spectrum of starlight, or detects particles inside a laboratory experiment. In this traditional view, the observer is separate from the universe. Reality exists independently, and science simply describes what is already there. But the strange discoveries of quantum mechanics gradually began to blur this separation. At the smallest scales, the act of measurement appears to influence the outcome of events. Particles behave like waves of possibility until a measurement occurs, then a single result appears. This curious feature led some physicists to wonder whether observation might play a deeper role in the unfolding of reality. One of the scientists who explored this possibility most deeply was John Archibald Wheeler. Wheeler was a student of Niels Bohr and later became one of the most influential physicists of the 20th century. He contributed to the study of nuclear physics, general relativity, and black holes. In fact, Wheeler helped popularize the very term black hole, which now feels so natural in our language of astronomy. Yet Wheeler also had a philosophical side. He often asked questions not only about how the universe works, but about why the universe appears the way it does. As he reflected on quantum mechanics, Wheeler began to wonder whether observers might play an essential role in the structure of reality. He proposed a concept that he called the participatory universe. The idea suggests that the universe is not a fixed stage where events unfold independently of observers. Instead, observers participate in the unfolding of reality through the act of measurement. To understand Wheeler's perspective, imagine again the quantum world of possibilities. Before a measurement occurs, a particle may exist in a superposition of several potential states. When a measurement takes place, one of those possibilities becomes actual. In everyday experiments, this process appears small and local. A detector clicks, a photon is absorbed, a measurement is recorded. But Wheeler wondered whether similar processes might operate at much larger scales. Perhaps the history of the universe itself emerges through countless acts of observation. In one of Wheeler's thought experiments, he imagined what is called a delayed choice experiment. In this scenario, a particle such as a photon travels through an apparatus that can measure either its wave-like behavior or its particle-like behavior. The surprising aspect of the experiment is that the choice of measurement can be made after the photon has already passed part of the apparatus. In other words, the experimenter decides how to observe the particle only after it has begun its journey. Yet the final measurement still determines whether the photon behaves as a wave or a particle. The result seems to suggest that the present choice of measurement influences how the past behavior of the photon is described. This does not mean that observers literally change the past, but it highlights something subtle about quantum reality. The description of events depends on how they are observed. Wheeler extended this idea into a grander picture of the universe. He suggested that the cosmos may resemble a vast network of interactions in which observation plays a creative role. Each act of measurement converts possibilities into actual events. Over time, these events accumulate to form the history of the universe. Wheeler once summarized this vision with a striking phrase. He described the universe as a self-excited circuit. In this poetic image, the universe gives rise to observers through processes of cosmic evolution. Then those observers participate in bringing the universe into definite form through acts of observation. The circuit completes itself. The universe creates observers, and observers help define the universe. To illustrate the idea, imagine a long novel whose pages are initially blank. Each time a reader turns a page and begins to read, the story on that page appears. The reader does not write the story alone, but the act of reading allows the narrative to unfold. Without readers, the pages remain empty possibilities. In Wheeler's vision, observers may play a similar role in the cosmic story. The universe may contain countless potential histories, and observation helps determine which events become part of the unfolding narrative. Of course, Wheeler's participatory universe does not imply that human consciousness is the sole source of reality. The universe existed long before human beings appeared on Earth. Stars formed, galaxies evolved, and planets emerged over billions of years. But Wheeler suggested that the process of observation might occur whenever physical systems interact in ways that produce definite outcomes. In this sense, observation might be woven into the very fabric of physical processes. The participatory universe remains a philosophical interpretation rather than a proven scientific theory. Yet it invites us to rethink the relationship between the observer and the cosmos. Perhaps consciousness is not merely an accidental byproduct of matter. Perhaps it participates, in subtle ways, in the unfolding structure of reality. This idea does not claim that the mind controls the universe. Instead, it suggests that observation and existence may be more deeply connected than classical physics once imagined. As we continue our exploration, another modern thinker will propose an even more radical perspective. He suggests that the world we perceive, including space and time themselves, may function more like an interface than the true foundation of reality. When you open a computer and look at its screen, you see a calm and orderly world. Folders sit neatly on the desktop. Icons represent documents, applications, and pictures. With a simple click of the mouse, you can move files, open programs, or delete items. Everything appears clear and intuitive. Yet behind that quiet interface lies a far more complicated reality. Inside the computer, billions of electronic events occur every second. Electrical signals travel through microscopic circuits. Layers of software translate instructions into patterns of voltage. The true activity of the machine is incredibly complex, far beyond what appears on the screen. The interface hides this complexity. It presents a simplified world, designed to help the user interact with the system efficiently. Donald Hoffman suggests that our perception of the physical world may function in a similar way. According to his theory, evolution favors organisms that perceive useful information, not necessarily accurate information. Natural selection rewards behaviors that help an organism survive and reproduce. If a simplified perception leads to better survival strategies, that perception may become dominant even if it doesn't reveal the deeper structure of reality. To understand this idea, imagine two hypothetical creatures living in the same environment. The first creature sees the world exactly as it truly is at the most fundamental level. It perceives quantum fields, complex molecular interactions, and the detailed geometry of space-time. The second creature sees only simple symbols representing opportunities and dangers. Perhaps food appears as a glowing green shape. Predators appear as red shadows. Safe paths appear as gentle, blue lines. Although the first creature perceives reality more accurately, its perception is extremely complicated. Processing all that information requires enormous effort. The second creature, by contrast, sees a simplified interface that highlights only what matters for survival. Green shapes mean food. Red shadows mean danger. Blue lines mean safety. In many situations, the second creature might actually survive more successfully. Its perceptions are efficient and action-oriented. Hoffman suggests that evolution would likely favour the simpler interface. Over many generations, natural selection might gradually shape perception into a system that hides the underlying complexity of reality. In this view, the physical objects we perceive may function like icons on a computer desktop. When you see a cup on a table, your mind interprets it as a solid object existing in space. But the deeper reality underlying that perception could be far more complex than our senses reveal. Hoffman does not claim that the physical world is an illusion in the ordinary sense. The objects we perceive still guide our actions and interactions. Just as a desktop icon allows you to manage files inside a computer, the objects of perception allow us to navigate our environment. But the icon is not the file itself. In the same way, the objects we perceive may not represent the fundamental structure of reality. If space and time are part of an evolutionary interface, then what lies beneath that interface? Hoffman proposes that the underlying layer of reality may consist of entities he calls conscious agents. A conscious agent in this framework is a system capable of experiencing and making choices. These agents interact with one another through networks of relationships. Their interactions generate patterns that appear to us as physical events within space and time. From our perspective inside the interface, we see objects moving through space. We observe particles colliding, stars forming, and planets orbiting their suns. But according to Hoffman's model, these events may be surface-level symbols representing deeper interactions among conscious agents. You might imagine it as watching a digital simulation on a computer screen. The characters in the simulation move across landscapes and interact with objects. But the true processes driving those events occur within the underlying code of the program. The characters inside the simulation cannot see the code directly. They experience only the interface. In Hoffman's proposal, our universe may function in a somewhat similar way. Space, time, and physical objects may represent the interface through which deeper processes become visible to conscious observers. These ideas remain speculative and controversial. Many scientists argue that physical reality exists independently of consciousness. They believe that the laws of physics operate whether or not any observer is present, yet Hoffman's perspective raises a thought-provoking question. If evolution shapes perception for survival rather than truth, how much of reality might remain hidden behind the interface of our senses? Perhaps our everyday experience reveals only a small portion of the deeper structures that make up the universe. The possibility invites us to think more carefully about what we mean when we say we observe reality. Are we seeing the universe as it truly is, or are we interacting with a carefully constructed interface that simplifies a far more complex world? As we continue our journey, we will encounter another interpretation of quantum mechanics that offers a very different answer to the mysteries of measurement and observation. Instead of collapsing into one outcome, this interpretation suggests that every possibility may continue to exist. And if that is true, the universe may be far larger and more diverse than our single experience reveals. For decades, the collapse of the quantum wave function has remained one of the most puzzling features of quantum theory. Physicists can use the equations of quantum mechanics to predict probabilities with extraordinary precision. Yet the theory itself does not clearly explain why a single outcome appears when a measurement occurs. Many interpretations attempt to resolve this mystery. Some suggest that observation causes collapse. Others propose that unknown physical processes force the wave function to reduce to one possibility. But Hugh Everett asked a different question. What if the wave function never collapses at all? Everett was a graduate student at Princeton University when he developed this idea. Instead of introducing a special rule for collapse, he proposed that the mathematical description of quantum mechanics should be taken seriously at all times. According to the standard equations, the wave function evolves smoothly over time. There is no sudden interruption, no abrupt selection of a single outcome. Everett suggested that this smooth evolution continues even during measurement. To understand this idea, imagine a simple quantum experiment. A particle approaches a detector that can record one of two outcomes. Perhaps the particle might appear in position A or position B. In the traditional collapse interpretation, the particle begins in a superposition of both possibilities. When the measurement occurs, the wave function collapses and the particle appears in only one location. But Everett proposed a different picture. When the measurement occurs, the system evolves into a larger superposition that includes both the particle and the measuring device. In one branch of the wave function, the detector records outcome A. In another branch, the detector records outcome B. Both outcomes exist simultaneously within the universal wave function. From the perspective of an observer inside one branch, only a single result is experienced. But the other branch continues to exist as well. In effect, the universe splits into multiple histories. Each history contains a different realization of the quantum possibilities. This idea has become known as the many worlds interpretation. The phrase does not necessarily mean separate universes floating somewhere in space. Instead, it describes a branching structure of reality. Every time a quantum event with multiple outcomes occurs, the universe may divide into different versions of itself. Each branch contains its own sequence of events, unfolding independently of the others. To visualize this idea, imagine a tree growing in a quiet forest. At the base of the trunk there is a single path upward, but as the tree grows, branches spread outward in many directions. Each branch continues growing, splitting again and again. In Everett's interpretation, the universe may resemble a cosmic tree of possibilities. At every quantum event, new branches emerge. Each branch represents a different history of the universe. From our perspective within one branch, we experience a single continuous story. But according to the theory, countless other stories may be unfolding at the same time. Most of these branches would be impossible for us to observe directly. Once branches separate, they evolve independently and rarely interact again. The many worlds interpretation solves one important problem in quantum mechanics. It removes the mysterious collapse of the wave function. Instead of requiring a special process that chooses one outcome, the theory allows all outcomes to exist. The mathematics remains simple and consistent. Yet this simplicity comes with a dramatic consequence. Reality may be vastly larger than our single experience suggests. Every quantum event could generate new branches of history. Over time, the number of branches might grow beyond imagination. Some thinkers have even speculated about a strange implication sometimes called quantum immortality. In certain interpretations of many worlds, if a person faces a life-threatening event with multiple possible outcomes, there may always exist some branch in which the person survives. However, such ideas remain controversial and speculative. Most physicists focus on the mathematical consistency of the interpretation, rather than these philosophical extensions. Even without such speculation, the many worlds interpretation raises profound questions. If every possibility exists somewhere within the universal wave function, what determines the particular branch we experience? Why does our consciousness follow one path through the branching tree rather than another? Some researchers have wondered whether consciousness itself might play a role in selecting or tracking particular branches. Others believe that consciousness simply follows the physical processes occurring within the brain, which themselves evolve within one branch of the universal wave function. The theory does not provide a final answer to these questions, but it reshapes the conversation about measurement and observation. Instead of asking why possibilities collapse into one outcome, we begin to ask how observers experience one branch among many. The many worlds interpretation reminds us that the universe described by quantum mechanics may be far richer than our everyday intuition suggests. Our experience may represent only one thin thread within an enormous tapestry of possible histories. As we move toward the final stages of our exploration, we will step back and consider a broader shift that has been unfolding in modern physics. A shift in which reality is no longer described primarily as solid objects moving through space. Instead, many scientists now see the universe as something more fluid, a vast network of information, relationships and processes continually unfolding. When we look at the world around us, it seems natural to think in terms of objects. A stone rests on the ground, a tree grows beside a river, a planet circles a distant star for thousands of years. This object-centered view shaped the way people imagine the universe. Even early physics followed this intuition. Isaac Newton described motion in terms of objects with mass moving through space under the influence of forces. In Newton's world, the universe resembled a vast mechanical clock. Each object had a position, a velocity, and a trajectory. If one could know all these details precisely, the entire future of the system could, in principle, be predicted. This image of reality proved extraordinarily successful. It allowed scientists to predict the motion of planets, design machines, and understand many natural phenomena. Yet as physics advanced into the 20th century, cracks began to appear in this mechanical picture. Quantum mechanics revealed that particles do not always behave like tiny solid objects. Instead, they often appear as patterns of probability. A particle may be described by a wave of possibilities rather than a precise location. Only when interactions occur do specific outcomes become visible. Gradually, physicists began to realize that the fundamental description of nature might involve something more subtle than objects moving through space. One emerging idea is that information may play a foundational role in physics. Information, in this context, does not simply mean messages written in books or stored on computers. Instead, it refers to the structure of relationships between physical states. For example, if two particles become quantum entangled, their properties are linked in such a way that measuring one instantly reveals information about the other. The particles may be separated by vast distances, yet the information connecting them remains intact. This strange relationship suggests that the universe may be deeply relational. Instead of existing as isolated objects, physical systems may be defined by the information they share with one another. Some physicists have taken this idea even further. They suggest that information itself might be one of the most fundamental ingredients of reality. In this view, particles and fields may emerge from deeper patterns of information. Just as the images on a computer screen emerge from patterns of digital data, the physical world we observe might arise from deeper informational structures. Another intriguing concept that appears in modern physics is known as the holographic principle. The idea emerged from studies of black holes and the strange way they store information. When matter falls into a black hole, the information describing the matter does not simply disappear. Instead, theoretical work suggests that the information may be encoded on the surface area of the black hole's boundary. To picture this idea, imagine a hologram printed on a thin sheet of film. The sheet itself is flat, yet when light shines through it, a three-dimensional image appears. In a similar way, some physicists believe that the information describing a region of space might be encoded on its boundary surface. The three-dimensional world we experience could emerge from information stored on a two-dimensional surface. Although this idea is still being explored and debated, it illustrates a broader trend in modern physics. Reality may be less like a collection of objects and more like a system of relationships and encoded information. Even space-time itself might not be fundamental. Some theories suggest that the geometry of space and time could arise from deeper networks of information. If this is true, then the familiar stage on which the universe unfolds may itself be a kind of emergent structure. Instead of beginning with space and time and placing objects within them, the deeper theory might begin with relationships. From those relationships, the appearance of space, time, and matter would gradually emerge. You might imagine it like a conversation taking place among countless participants. Each participant exchanges information with others. From the pattern of those exchanges, a larger structure begins to form. The conversation itself becomes the fabric of the system. In this metaphor, the universe resembles a vast dialogue of interactions rather than a warehouse filled with objects. Particles are not simply things, they are events within a network of relationships. For researchers interested in consciousness, this shift in perspective opens intriguing possibilities. If reality is fundamentally informational and relational, then consciousness might also relate to these deeper patterns. Some thinkers wonder whether conscious experience might involve the way information flows and integrates within complex systems. Others speculate that consciousness could be connected to the informational structure of the universe itself. These ideas remain speculative, yet they reflect an important transformation in the way scientists think about the nature of reality. The universe may not be built from solid pieces like the gears of a clock. Instead, it may resemble a living tapestry of relationships, processes, and information continually unfolding. Within that unfolding tapestry, observers like us appear. We observe the universe, ask questions about its origins, and reflect on our own existence. And perhaps in doing so, we participate in the ongoing process through which the universe becomes aware of itself. This possibility brings us gently toward the final reflection of our journey. After exploring quantum puzzles, theories of consciousness, and the deep structure of reality, one quiet question remains. What if consciousness is not merely a product of the universe, but part of the way the universe understands itself? Throughout our journey, we've explored many ideas that challenge our everyday intuition. We began with the strange behavior of the quantum world, where particles exist not as fixed objects, but as waves of possibility. A particle may appear to occupy several potential states at once, like a quiet chord containing many musical notes waiting to be played. Only when an interaction occurs does one of those possibilities become part of the visible world. From there, we encountered the measurement problem. Physics provides remarkably accurate equations describing how quantum systems evolve. Yet the theory leaves open a mysterious question. What exactly causes possibilities to become definite events? Some interpretations suggest that measurement devices trigger this transition. Others wonder whether conscious observation plays a role. Still others propose that every possible outcome continues to exist in branching histories of the universe. Each interpretation offers a different way of understanding the same mathematical framework. None has yet provided a universally accepted answer. Along the way, we turned our attention toward the brain. The brain is an astonishing structure containing billions of neurons, each communicating through networks of electrical and chemical signals. Through these interactions arise thoughts, memories, emotions, and the rich inner landscape we call conscious experience. Many neuroscientists believe that consciousness emerges naturally from the complexity of these neural networks. As patterns of activity become more integrated and dynamic, subjective experience appears. Yet even with advanced brain imaging technologies, one puzzle remains unresolved. Scientists can identify the neural processes that accompany conscious experience, but explaining why those processes feel like anything at all remains deeply challenging. Why does a particular pattern of neural activity produce the experience of colour? Why does pain feel painful rather than simply triggering a mechanical reaction? These questions are sometimes called the hard problem of consciousness. They remind us that describing the physical mechanisms of the brain is not quite the same as explaining subjective experience. Some researchers have explored the possibility that deeper physical processes may be involved. Roger Penrose suggested that human reasoning might involve non-computable processes connected to quantum physics. Stuart Hameroff proposed that microscopic structures inside neurons, called microtubules, could host delicate quantum states. Their theory, known as orchestrated objective reduction, attempts to connect the collapse of quantum possibilities with moments of conscious awareness. Whether this theory ultimately proves correct remains uncertain, but it illustrates how scientists are willing to explore ideas that bridge physics and neuroscience. We also encountered discoveries from the field of quantum biology. Experiments suggest that plants may use quantum coherence to guide energy through photosynthesis. Migratory birds may sense Earth's magnetic field through delicate quantum interactions. Certain enzymes appear to use quantum tunneling to accelerate chemical reactions. These discoveries remind us that the boundary between physics and biology is more subtle than once imagined. Nature often uses the most efficient processes available, even if those processes seem strange from a classical perspective. Later, we widened our view to the scale of the cosmos. Physicist John Wheeler proposed that observers might participate in the unfolding of reality itself. In his participatory universe, observation becomes part of the process through which possibilities become actual events. Donald Hoffman offered another perspective, suggesting that our perception of space and time may function like a user interface shaped by evolution. Beneath that interface, reality might consist of deeper networks of interacting conscious agents. The many worlds interpretation introduced yet another possibility. Instead of collapsing into one outcome, the universe may continuously branch into multiple histories. Each branch represents a different realization of quantum possibilities. Our experience follows one path, through that immense tree of potential realities. Finally, we explored the growing view within physics that reality may be built not from solid objects but from information and relationships. Particles may be understood as events within networks of interaction. Space-time itself might emerge from deeper patterns of information. In this picture, the universe resembles a vast tapestry of processes continually unfolding. When we gather these ideas together, a quiet possibility appears. Perhaps consciousness is simply a natural consequence of complex biological systems. In that case, minds arise when matter organizes itself in sufficiently intricate ways. This view aligns with much of modern neuroscience. But another possibility remains open. Perhaps consciousness reflects something more fundamental. Perhaps experience is woven in subtle ways into the fabric of reality itself. Some philosophers call this view panpsychism. Others speak more cautiously of consciousness as a basic feature of certain physical processes, and there may be possibilities we have not yet imagined. At present, science does not provide a final answer. What it offers instead is a growing understanding of how mysterious and intricate the universe truly is. From the smallest quantum fluctuations to the largest cosmic structures, reality continually reveals layers of complexity. Within this vast unfolding universe, small islands of awareness have appeared. On a quiet planet orbiting an ordinary star, minds have evolved that can wonder about the cosmos. Through those minds, the universe reflects on its own existence. Perhaps that is the most remarkable discovery of all. You are part of a universe that has learned to ask questions about itself. Each thought, each moment of awareness, is a tiny window through which the cosmos looks back upon its own story. And whether consciousness arises purely from matter, or whether it reflects something deeper in the structure of reality, one thing remains certain. The universe is not silent. Through living minds it has begun to speak, and in the quiet space of your own awareness it continues to listen.